One of them is somewhat controversial because it doesn't apply always, but I will show you the famous example. This is the reactivity selectivity principle. And the idea is that they're opposed to each other, that something that is highly reactive will not be selective, and something that is selective might not be highly reactive. And the classic example of this is in the following radical type reaction. So if you do radical chlorination of this hydrocarbon, you've got two different kinds of protons, and so your products will be either chlorination here or chlorination there. And then you can do the same thing for radical bromination and get the same analogous products. The issue is there selectivity between these two products? And for chlorine, I guess this was a bad, yeah, that's a bad example. Let me check and make sure, because there was supposed to be an example with secondary stuff in it, so I want to make sure I get that. Yes, okay, sorry. So we're just going to add a methyl group. So there would be, in addition to these two products, there would be the primary chlorination product. Everybody see what I did there? I just added a methyl group. So you have three different kinds of hydrogens. You have a tertiary hydrogen, secondary, and a primary hydrogen. And then in your product, you've got a tertiary alkyl halide, a secondary alkyl halide, and a primary alkyl halide. And for chlorination, the ratio is 6 to 4 to 1. But for bromination, it's 19,000 to 200 to 1. And so you'd say that bromination is far more selective. And what's the rationale for this? Well, one of the intermediates along the pathway is a carbon-centered radical. So you've got this tertiary radical that leads to these products. You've got this secondary radical that leads to these products, and then you've got a primary radical that leads to the product shown above. And in terms of radical stability, we think of radicals as being electron deficient, so the tertiary radical should be more stable, either because of hyperconjugation or because electron donation by the neighboring alkyl groups. And primary radical is going to be less stable. And the idea here that people try to summarize is just that, well, chlorine radical is more reactive than bromine radical, and therefore chlorine, because it, and then they tend to anthropomorphize molecules and say, well, chlorine, because it wants to react so bad, will not be selective. And I've heard analogies like, well, if you're really hungry and then you go shopping, you will be less selective about what you put in your cart than if you go when you're not hungry. But that's not really a rule of thumb you can apply. What's going on is probably here, it's probably an expression of the Hammond postulate. So I'm going to plot on the same axes. This y-axis is energy, and then x-axis is going to be reaction progress. And we have our starting material. And I'm just going to illustrate this with a simpler starting material. Got two different kinds of protons there. Chlorine radical is more reactive than bromine radical. Again, that has to do with size, in the same way that Cl- is a stronger base than Br-. So they're both really weak bases. So, and both of them come to, the first reaction is hydrogen abstraction from a radical to remove either this proton or that one. So afterwards, the products are going to be either HCl or HBr, which probably in organic solvent have similar stabilities, and a secondary radical. So we basically end up in the same place. And then I suppose there's an alternative product up here, which is the primary radical. So we'll maybe move chlorine up a little bit. So I'm going to use the color red for the reaction diagram for chlorine going to like the secondary product. So there's a transition state, and then there's the secondary product, okay? And to a lesser extent, you know, here's the primary product. And what I'm showing you is really the radical intermediate, because this is going to go on and give us there's going to be a subsequent reaction where we abstract a chlorine from Cl2. You guys recognize that reaction? No. Okay, so I'm only dealing with the radical intermediate, but let's see how the reaction is for bromine. For bromine, these reaction steps are actually endothermic. Oh, holy Toledo, Batman, that's not the right thing. Okay, uphill for bromine, downhill for chlorine. Now, what does the Hammond postulate tell you about the transition state for bromination, for radical bromination? What does it look like? Does it look like starting material or products? So in blue, it's a late transition state, right, for bromine. So that transition state should be very radical-like. And that's just Hammond postulate, right? So it would make sense then that if the transition state is radical-like, the transition state leading to the more stable secondary radical should be lower in energy than the transition state leading to the less stable primary radical. So for bromine, it should be faster to give you the secondary radical, and you should see some selectivity for the secondary radical. In contrast, there's probably not a lot of variation in the transition state for chlorination, because that transition state is much closer in energy to your starting materials. It is not radical-like, and the starting materials are really the same for these two, to lead to these two products, only we're reacting with different protons. So there's not a lot of difference between the pathway that leads to the primary versus the secondary radical. Yeah?
So basically one splits its tails, the other splits its peaks.
Right. Right, one splits its tail, the other splits its peaks. And this has to do, again, with the proximity of the transition state in energy to either starting materials versus products. Okay, questions about that? So you could probably think of situations where the reactivity selectivity principle wouldn't apply. So you don't want to apply that as a general rule, but you'll hear people use it as a potential explanation, and just know that when they do that, you'll have an idea of what assumptions they're making, and the assumptions they're making are likely that they're in a situation where the Hammond postulate applies, and that the transition state for the reaction is closer in energy to the high energy intermediate for a process that's selective. All right, any more we want to say about that? I don't particularly want to, so we can move on. All right, the next principle is called the Curtin-Hammett principle, and it's confusing because we just got done talking about the Hammond postulate, and now we're talking about the Curtin-Hammett principle. Later on in the class, we're going to talk about things called Hammett parameters. If you forget which is the Hammond postulate and which is the Curtin-Hammett principle, you just have to slur your words a little bit and you can use the same. So it's the Hammond postulate and the Curtin-Hammett principle. And it sounds like you know what you're talking about no matter what. So the Curtin-Hammett principle is related to a process, two competing processes, and their products. So let's imagine a rapid and reversible equilibrium between two starting materials or two intermediates, and there's some equilibrium constant. And we'll also make an energy diagram here. So we'll suppose that one intermediate is a little higher in energy than the other. But that, both at equilibrium, both intermediates are populated. Now, let's suppose that intermediate 2, which is more stable, goes through a high energy transition state to lead to a product. We're not going to really say anything about product stability. This will be product 1. And we'll say that intermediate 1 goes through a lower energy transition state to give product 2. And again, I'm intending to communicate that we're not saying anything about product stability. And there's a reason why we're not. So you've got the transition state. Oh, you know what? That's totally crazy and backwards, right? Somebody should have told me, why should intermediate 2 lead to product 1? That's just too dang confusing. So we'll let this be product 2. And then over here, that'll be product 1, right? So this is the transition state that leads to product 2. This is the transition state that leads to product 1. And we'll say that both of these reactions are such that they are irreversible, meaning we've got enough kinetic energy to go over this hill, but we can't go backwards. All right? So under irreversible conditions, product stability doesn't matter at all. The products are not in equilibrium with starting materials, so their stability really doesn't matter. But the idea behind the Curtin-Hammett principle is that when you have two common intermediates that can lead to two different products, and if the reaction is irreversible, the final ratio of one product to another should not depend heavily on this equilibrium, but rather will depend more on the relative rates of going over this hill versus that hill. So you can do some math and calculate the ratio of product 2 to product 1. And that's going to equal, the equilibrium constant is in there, but that's going to equal the rate constant for going over this hill, K2 times the concentration of intermediate 2 versus K1 times the concentration of intermediate 1. And if you've got this equilibrium where the equilibrium constant is somewhere, like 1 or maybe low sort of 2 or 3 or something like that, whereas the relative rates are different by, you know, multiple factors of 10, the outcome is going to be mostly determined by,
It's supposed to be K1 on the bottom.
yes, thanks, sorry, yeah. Reaction outcome is mostly influenced by relative rates, which is basically transition state energies, and not by intermediate stabilities. Okay, so let me give you an example of when this is the case. We're going to consider addition of a nucleophile to the following, we'll say, ketone, where the ketone has, oops, that was an eraser, I didn't want that, a large group here, a small group. Well, how do I want to do this? It's got sort of a medium group here, a large group here, and a small group there. And you'll recognize this as a stereocenter, which means that the top face and the bottom face of this ketone are diastereotopic, which means there can be some selectivity for one versus the other. So we're going to actually look at this ketone on its edge so you can see the difference between both of those faces. And I'm going to draw, we're looking at the sp2 hybridized carbon, so here's that R group, and then for this alpha carbon in the back, we've got, right now it looks like the medium group here, a large group here, and the, wait, sorry, look, it should be out to our right, and then the small group here. And you could imagine that there might be some conformational equilibria as we rotate around the bond between carbonyl carbon and alpha carbon. There's a few unique conformations we could draw. What about the small group here, and then the large group here, and then the medium group there? Alternatively, we could draw a conformation. I need a little bit more space. And then we could rotate again to generate the third and final conformation, which might have the large group here, the small group here, and the medium group there. All right. So we might be tempted to ask ourselves which of these conformations is the most stable, and then, and only then after that, consider where the nucleophile should attack from. For example, if, say, this conformation were more stable, and I'm not sure, maybe this is the most stable conformation, then maybe you would have to decide, okay, where does the nucleophile attack from? From the side that has the medium group or the side that has the larger group? And but it turns out you don't even need to worry about which is the lowest energy conformation. You simply need to worry about which is the fastest route of attack. Sorry, just a second. So what we'll say is I need to adjust my drawing. I showed a group eclipsed with the carbonyl, and actually a better representation of that would be, there's a group sticking out straight and then a couple of groups like this. That's probably a better conformation. So what I'm describing here is the difference between these three choices. Sorry about that. Questions you want to ask there? Probably, we didn't necessarily talk about conformations of ketones and alpha carbons. Probably where you have one group perpendicular to the ketone is better because of orbital overlap. You can overlap a carbon-carbon bond with a pi star or with a pi system, so if these are the conformations, and this is probably the best you can do in terms of avoiding eclipsing interactions, you might be tempted to say, well, this conformation is better because the large group is farther away from these two. On the other hand, you might say, if a nucleophile had to choose which of these conformations to react with, it's probably fastest to react from this perspective where it approaches the small thing and only the small thing. Do you see how otherwise, if it approaches from this side, that's, if you approach from the side that has two things, that's more sterically hindered. So you want to approach from the side that has only one thing. And of your three choices, this one's probably the fastest. Curtin-Hammett principle here says this is the one that's going to lead to product, the major product, because this is the attack that is the fastest. So we don't care which conformation is most stable. It's not going to affect the product ratio that much. If these equilibria are, if each of these is populated significantly, and the conversion from one to the other is reversible, but the reaction of the nucleophile attacking is not reversible, then the fastest product to form wins, and you don't have to consider stability of the intermediates. Okay, anything I want to ask about that? I got off track because I'm tempted to think about the stability of the intermediates. I draw Newman projections and I'm like, well, which one of those is most stable? I don't know, and start to think. I might think this one actually, but it turns out that only the fastest to form matters when the reaction is irreversible. All right. Couple other principles. Let me look at time. Good. One is a principle called microscopic reversibility. We don't need to say a lot about this, but reaction pathways have to be the same in the forward and reverse directions. Reversibility. That means if I go from starting material to product via this pathway, if I go back from product to starting material, I have to go back via the exact same pathway and not some other weird alternative. Right, because your pathway is the lowest trajectory between two different wells on the energy landscape, and the forward and reverse paths have to be exactly the same. Okay, another concept you will hear, so that was 4, another concept you will hear is kinetic versus thermodynamic control, and I think people make this more complicated than it needs to be. The idea is, first, if the reaction is irreversible, fastest to form product is the major product, period. Product stability doesn't matter. In contrast, if the reaction is reversible, that means it's in equal, starting material and products are in equilibrium, then the most stable product is the major product. So it's as simple as that. Are you doing the reaction under conditions that are irreversible or conditions that are reversible? This shows up most, I think, in enolate type chemistry that you'll teach undergraduates about if you're a TA. And you've probably heard of the kinetic versus the thermodynamic enolate. It's not like you're going to look at a situation and be like, oh, that's the kinetic product and that's the thermodynamic product. It just has to do with whether the reaction's reversible or not, and if it's reversible, then you get the most stable product. If it's irreversible, you get the product that's fastest to form. You may find situations where the product that's fastest to form is also the most stable product. The E2 reaction is an example of that, where you get the most stable alkene even though the E2 reaction is basically irreversible. All right, 6, and I think this is last on our list of principles to apply, is a concept called effective molarity. And this concept is basically related to pre-organization. It's that intramolecular reactions are faster. Intramolecular reactions are faster than intermolecular reactions. And the idea is it's almost like you get an effective bonus in concentration when you do an intramolecular reaction. So let me try to give you an example of this. Suppose we have a molecule like this squiggly line, and we've got an iodide or a leaving group at the end of it, and we've got an amine at the other end of it. And we'll call this starting material, I don't know what we're going to call it. Your text calls it starting material I. There's a couple of things that could happen. You could do an intermolecular reaction where one molecule of I finds another molecule of I to give you a linear product. Okay, see how we could get that? The rate law we would write for that would be some rate constant K. We'll use 1. I think we'll actually use 2 because this involves 2 molecules of I, and the rate law would be like this, right? In contrast, you could do a unimolecular reaction, K1 times I, to get a cyclic product like this with iodide as the leaving group, all right? So if you want to know the rate of the formation of cyclic product 1 versus linear product 2, that's going to equal K1 times I divided by K2 times I squared. And we'll cancel out one of the terms of I, and this ratio of rates is going to equal K1 divided by K2 with I in the denominator. That's the ratio of cyclic versus linear. And if I is in the denominator, ratios are dimensionless. So what that means is that K1 over K2 has units of molar. concentration. And this is what we call effective molarity. That is, you can't make a direct comparison because this is unimolecular versus this is being bimolecular, but this number tells you basically how much faster or more effectively you form the cyclic product, and it's as if there's some increased concentration of the two groups relative to each other. And this makes some amount of sense. You can actually probably calculate it theoretically if you have the distance between these two groups and the volume traced out by that molecule. Those two things are constrained to be within that volume, and that is a higher effective concentration than if they're just free in solution. So you'll hear people talk about that. Most of the time when they talk about effective molarity, they're just talking about the two groups are constrained to be in the same sort of space, and so it's like they're really concentrated. But there is a more technical definition, and it's this one. But the most you'll basically hear the concept the most in explaining why intramolecular reactions are faster than intermolecular reactions. All right. Yeah.
Is there a way to tell which to lead to, if it will lead the cyclic product or the linear product?
Is there a way to tell whether
It will lead to the cyclic product or lead to the linear product?
right? So you would predict. So what the ratio? This is what that ratio means. And it's going to depend on what these rate constants are, but as you can see, it's also going to depend on the concentration. You might predict that if I increase the concentration of my starting material, that should accelerate this reaction more than this reaction, right? Because this reaction has an I squared term, so concentration affects this reaction a lot. It affects this reaction too, but to a lesser extent. So when you go to do a cyclization reaction, the concentration of the starting material matters. If it's too high, you might start to see linear product. So if you see linear product, or maybe you see lots of different products, linear product that has cyclized, or perhaps multiple linear products as a polymer. People worry about this all the time when making macrocycles. So the solution, one of the solutions people use is, let's lower the concentration. Let's make it more dilute. Yep. Another thing they do is, well, if I could bring, it's the concept of pre-organization. If I could put in another molecule that sort of would template this molecule to bring those two things together close to each other, then I could accelerate the reaction. People do that too.
So what about this ratio? If this ratio maybe increases or reduces, does it have anything to do with which of the rate constants is higher? No,
though it does tell you that you get
because
independent of what.
If K1 is larger,
yeah,
this effective molarity will probably be
high. Yeah.
And that, which means that is it coming towards this direction?
Yeah, I mean, if K1 is higher than K2, then yeah, you're going to get more product 1 than product 2. Yeah. But the idea here is just that whatever K1 and K2 are, the number you get by dividing K1 by K2 has units of molar, and you can think of it as an expression for how concentrated these two groups are in the same molecule.
So we cannot back calculate. For example, we're given the effective molarity as a figure.
Yeah.
Can it be back calculated to tell where it went to?
If you have effective molarity and you know concentration, I still don't know. You need some more information to solve for the individual rates. But if you have effective molarity, you can definitely tell which is faster, right? If effective molarity is greater than 1, that tells you that it's faster to get the cyclic product. If it's less than 1, that tells you it's slower. All right. Well, let's see. So now we're going to go back to some math. Yay! It's your favorite part. We're going to learn to.
Not a favorite part.
This is gonna be a pain, but when we're done, you're gonna have the skills to understand catalysis papers and proposed mechanisms of reactions.
Dr. Bryce, hope it's not another chapter 14.
I hope so too. I hope it's not another chapter 14 too. So, we're gonna start simple. Simple is boring, but it'll be a review. This is first order kinetics. First order kinetics means there's only one molecule involved in the rate determining step. And here is a rate constant K, and we go from starting material A to products. Now, the rate of the reaction we can represent as either the disappearance of starting material or the appearance of product as a function of time. So one way to represent that is if you take the change in product versus the change in time. You could think of that as the first derivative of product concentration with respect to time. And if we're measuring this rate by product appearance, because there's only one place for product to come from, it would also be true to say the opposite of starting material disappearance is equal to that rate, okay? And then we know how to write rate laws, and for this first order reaction, that should be constant K times the concentration of A. And what we have done is actually given ourselves a differential equation. Which, why on earth would we have done that? I don't know a huge amount about differential equations, but they occur when you have a derivative of a quantity that is equal to some number and then that quantity itself. So you have both a derivative, this is like having the first derivative of x and x in the same equation. So the way you solve this, what we would like to have is a law that tells us what the concentration of product or starting material is as a function of time. And so what you can do is we try to get all of the terms that have all of the A terms on one side of the equation and all of the time terms on the other side of the equation. So if I multiply both sides by, divide both sides by the concentration of A, and then I multiply both sides by -1, I can get this expression. All right? And then I can integrate this side from some starting concentration of A at the beginning to whatever concentration of A we are at a particular time. And then I can integrate this side from time 0 to whatever time I'm interested in. And what we're going to do now is just calculus, and you don't necessarily need to know time t minus 0. The integral of 1 over x is the natural logarithm of x. So this is going to be the natural logarithm of the concentration of A minus the natural logarithm of the concentration of A at the start of our reaction. All right, and then we get just a little bit lazy because we don't like natural logarithms. So we're going to use a quick property of natural logarithms, of logarithms in general. The difference between two logarithms is the same as the logarithm of the ratio of those two numbers. And then we're going to raise both sides to the power, we're going to use both sides as exponents for the number e. All right? So the exponential of a natural logarithm, or e raised to the power of a natural logarithm, is simply that number. and then you've got E raised to the minus KT. And so then a final form of this equation is that a concentration of A at any time equals your starting concentration of A multiplied by the number E raised to the minus KT. Right? So that's a first order rate law, and if you were to plot this out, what you would have, concentration of A and then time, and you're going to see exponential decay. All right? And that applies in a lot of interesting situations. What you typically do to measure this rate, and we're done, yep, is you'll do the reaction at multiple concentrations of this starting, well, we'll talk more about that later. So that was the easy one. The other ones are hard. All right. Thank you for indulging me in my Darth Vader cosplay.